So lesson 3 in chapter 6 is about vectors in the coordinate plane, and vectors is probably going to be a new concept for most of you. So first of all, let's talk about basically what a vector is. Okay, so for a lot of things in math, like temperature, area, time, they're just one value, right? Just one number. But for some things like velocity or force, you have two things you've got to consider. You've got the magnitude or the amount of something, and you've also got the direction. So, we can throw a baseball and the speed it's going at is important, but the direction it's going in is important also. So whenever we've got something that we need to factor in its magnitude or its, velocity or its, its length and the direction, we use a vector. Okay, so first one we talk about is a directed line segment, which is essentially what a vector is. A directed line segment is just a line segment that has some kind of, it's got a specific direction to it. Okay, so that could be a directed line segment right there. Now, whenever you have a directed line segment, let's say this was point P that it starts at and it ends at point Q, then we would denote that directed line segment as PQ, and we'd put an arrow over it, but it's just kind of going to have one point on the arrow instead of an arrow on the top and the bottom. So that's how we would denote a directed line segment. The initial point it starts at is point P, and the point that it stops at is called the terminal point. Okay, so you got your initial point would be P right here, and Q is the terminal point. So this indicates something that has magnitude or length, right? It's got a certain length, and it's got a specific direction that it's going in. So the magnitude of this directed line segment is denoted by this right here. So if you see that, that's referring to the magnitude of it. And those are basically, they look kind of like absolute value bars around the directed line segment. So that's talking about the magnitude or the length of the directed line segment. And you can find that magnitude or length by using the distance formula, which we'll work on here in a second. Okay, so once you have a directed line segment, it's important to understand that any directed line segment that has the same direction and the same length, even if it's in a different location, is the same line segment as this one. So if we had over here, RS, all right, but if that has the same length as PQ and it's also got the same direction, then those are the exact same directed line segments. Even if they're in a different location, we think of them as the same. Okay, so whenever that happens, we can call them any directed line segments that have that same direction and that same magnitude, we can call a vector, like the same vector. And usually you see vectors denoted by using a lowercase letter that's in bold. So, when you see it on paper, it's usually going to be a little bit more bold. So it's usually V, you'll see U used a lot for vectors, W, some of those letters towards the end of the alphabet. But we try to stick away from like X and Y because those are usually coordinate points. So V, U, W are real common to see for vectors. All right, so let's go ahead and look now at equivalent directed line segments. So this says let U, which is a vector, be represented by the directed line segment from 0, 0 to 3, 2, and let V be represented by the directed line segment from 1, 2 to 4, 4. Show that U equals V. So like I said, if you've got the same direction and the same magnitude on directed line segments, then they're equal to each other. Okay, so let's draw P to Q. So 0, 0 to 3, 2. That'd be P, this would be Q. And we remember that P is the initial. It says from P to Q. And then we've got another one at 1, 2. And S is 4, 4. So we've got R to S. Right, and this is, of course, vector U, and this is vector V. So we're going to try to determine if these are the same or not. So we're going to try to show that they're equal. So what we got to do is first figure out, do they have the same magnitude? All right, so let's figure out the magnitude for PQ. To do that, use the distance formula. The distance formula, you're going to do the square root, and you're going to subtract the x coordinates. So the x-coordinates are 3 minus 0 squared. And you're going to add and subtract the y-coordinates, 2 minus 0 squared. So that gives us the square root of 3 squared plus 2 squared, which is 9 plus 4, which is 13. Now let's find the magnitude of RS. So we're going to do the same thing, subtract the x's, so 4 minus 1 squared plus 4 minus 2 squared. And we get, again, 3 squared plus 2 squared, which is the square root of 13. So we see that the magnitudes are equal. So that's the first step. Now you got to check and make sure the directions are equal. If the directions are equal, then we know that those two vectors are the same. So to figure out the directions, you just calculate their slopes. So slope is rise over run. So the slope of PQ, you go up 2 and over 3. And then the slope for RS is up 2 and over 3. So you can see that they've got the same slopes. So since those slopes are equal and their magnitudes are equal, we know that yes, U does equal V. Okay? So see if you can do this one down here. Check and see if these are the same directed line, same if they're the same vector. All right, so whenever we find the magnitude of vector U and vector V, we get the square root of 17 for both, which shows they got the same magnitude, or the same length. And then we find the slopes by doing rise over run, and they both have a slope of 1/4. So they both have the same direction, and they both have the same magnitude. Therefore, they are the same vector, so we can say, yes, U does equal V. All right, so moving on, talk about the component form of a vector, which is usually the way you'll see a vector expressed most often. So if we're given the initial point and the terminal point of the unit vector, it's a very simple way to figure out the component form. The component form, you're just going to subtract the x's. So 4 minus -1. Sorry, you've got to start with the terminal point, my fault. -1 minus 4. So you're always going to subtract the x-coordinate from the terminal point minus the x-coordinate from the initial point, and the same thing with the y-coordinate. So the terminal point is -5 minus, and the initial point is -7. Okay, now we express a vector, we use V right here, and then what we always see on a vector, you see it almost looks like a greater than or less than sign, only a little bit bigger. So we use those around vectors when we've got them in their component forms. Now, essentially what the component form of a vector tells us is the distance from the x-coordinates and the distance from the y-coordinates. So it kind of gives us an idea of both direction and the magnitude of the vector. So -1 minus 4 is -5. So that tells us the distance from the initial point to the terminal point on the x-axis is -5. And then -5 minus -7 is +2, which is the distance between the 2 points on the y-axis. All right, so that right there would be an example of the component form for this vector. So, if you graph those points, then essentially that is your run and your rise, right? -5 would be how far you run, 2 would be your rise. But that's usually the typical way you're going to see a vector expressed. So another thing you can do at this point is find the magnitude. So if it says we want to find the magnitude, so to find the magnitude of V, once you have the component form, is you just do square root, but now you don't have to subtract the x's, subtract the y's, you've already done that. So you can just square and add the two parts of your component form. So the magnitude of this is going to be 25 plus 4, which is 29. Okay, so that's the magnitude of vector V for this problem right here. All right, so was that right? Oh, I did -5. My fault. That's +5. 5 minus -7 should be 12. So you got 12 squared, which is really going to be the square root of 169. My fault, which ends up giving you 13. Sorry if you got to erase that. Right, I caught my mistake though. So there's your magnitude of that vector, and the component form is -5, 12, not -5, 2. Now, so see if you can find a component form and the magnitude of this vector right here. All right, so you can see the component form for this vector, v is -3,2, and the magnitude is the square root of 13. All right, so let's go on and look at vector operations, so adding, subtracting, multiplying vectors. All right, so first let's look at how to graph a vector. So if we look at the vector v, which is -2, 5, then if you draw that, the standard position of a vector is initial point being at the origin. So you can see this vector right here on the left would be vector v, okay, because it starts at the origin and it goes left -2 and up 5. Okay, so you're just using those x and y coordinates right there as an indication of where the terminal point is. So then w, of course, is over here at 3, 4 over 3 and up 4. So a couple things to understand about vector operations. Okay, if you ever multiply a vector by a constant, it just multiplies both the x and the y coordinate of the vector. So for example, 2 times v, so you just have 2 times -2, 5, which is going to give you -4, 10. So essentially what that does is just doubles the vector. It still has the same direction, but it's just going to double the length of the vector. So it would be like taking our vector v and extending it out all the way to the point -4, 10. It just doubles the length of it. Okay, so anytime you multiply a vector by a negative, that just changes the direction. So it basically would be like flipping the arrow around and putting the arrow at the other end. So the initial point becomes the terminal point, and the terminal point becomes the initial point. So if you just do -v, then -v would just make it start up at the point -2, 5, and the direction will be coming down to 0, 0. All right, so let's look at adding or subtracting real quick. So w minus v, it's pretty self-explanatory. You're just going to subtract the x coordinates and subtract the y coordinates. So we would have w, which is 3, 4, minus -2, 5. So you would subtract 3 minus -2 would be 3 plus 2, which is 5, and 4 minus 5 would be -1. So that would be w minus v if you do it algebraically. And then v plus 2w, of course you're going to take the v vector, -2, 5, and you're going to add on 2 times the w vector, 3, 4. So that's -2, 5, plus 6, 8. So when we add those, we get 4, 13. Alright, now that's how you would do it algebraically. But let's look at doing those graphically. Okay, so doing those, or geometrically, if we talk about doing it on a graph. So whenever you want to subtract w, do w minus v, essentially what you're going to do is you're going to have the w vector, okay, and then what you want to do is put the vector you're subtracting or adding, its initial point is now going to be at the terminal point for w. Okay, so let's see if I can get this vector here to move. Alright, so let's get these vectors where we want them. So we got w, and then if we do minus v, remember minus v would flip this around, right? So if we took this and changed the arrow, I can flip it. And flip it again, maybe. See if that'll do it. Yeah, so that just flipped it around, so now the arrow's in a different place. So if you do w minus v, you're going to take the w vector, and then you're going to, at its terminal point, you're going to put the initial point of the minus v vector. So minus v vector would be right there. Okay, and so here's what's kind of cool is when you do that, the vector that's the answer, w minus v, is the vector that connects those two, the initial point of w and the terminal point of the minus v vector. So you can see right here, if we connect these two, that is w minus v. So you've got w right here, Right here you've got minus v, and then down here is w minus v. So that's one thing that's kind of cool about adding and subtracting vectors is if you do it, you can do it with a graph or you can do it algebraically. So once I connect those, I'll see, oh, well, that's going right 5 and down 1. So 5, -1 would be the vector for that. Okay, you can do the same thing for v plus 2w. You can start with your v vector and then double the length of the w vector. Okay, so let's start with v. Flip this around. Did I flip that right? Yeah. So start with the v vector. And then from there we're going to do 2w. So w is normally right there. So let's double the length of it. So I'm going to go up 4 more and over 3. So that's 2w. All right. Let's get this over here out of the way. Sorry, it's a little tough on this graph sometimes wanting to click the right thing. So there's v, and then we're going to add on 2w, right, which would be right there. And so now you can imagine if you draw a vector connecting those from here to here, you're going to go up 13. Oh, I dropped it. So you're going to go up 13 on that vector and over 4. Right, so that would be your v plus 2w vector, over 4 and up 13. So that's kind of how you can do vectors when you're doing them on a graph, geometrically or algebraically. Yeah, algebraically is very simple, but you might have to understand doing them geometrically. So down here, practice doing them algebraically, and then we'll go over it. Alright, so right here you should have gotten the vector v instead of w, so you might need to correct that in your notes. But for A part, the vector you should get is -3, 1. For B part, it's -13, 1. And for C, you should have gotten 23, 9. Alright, so let's move on and talk about unit vectors. A unit vector is essentially a vector that's going to have the same direction as the original vector that you're given, but the magnitude of it is going to be 1, or the length of it is going to be 1. So what we've got to do to figure out a unit vector is to find the unit vector, you're going to use this little formula here. Just take the vector. It's pretty simple. Just take the vector and you're going to divide it by its magnitude. Okay, and once you divide it by its magnitude, it will give you a vector going in the same direction that just has a magnitude of 1. So our vector is -2, 5. And on the bottom, we're going to find the magnitude of it. So we do the square root of -2 squared plus 5 squared. That's -2, 5 over. And when we simplify that, we get the square root of 29. So then we've got -2 over square root of 29 and 5 over the square root of 29. And of course, we can't leave the square root on the bottom. So we've got to move the square root up top. On the bottom, leave 29. Same thing right here, 5 square root of 29 over 29. So this would be our unit vector. Okay, this vector is going to go in the same direction as -2, 5, but now its magnitude is just 1. It's just 1 unit long. All right, so the second part says to verify that it has a result, has a magnitude that is just 1. So to verify that, we're going to take this new vector we found, this unit vector, and find its magnitude. And its magnitude should be 1. So we'll use the same formula, the square root of, and we'll do -2 square root of 29 over 29 squared plus 5 square root of 29 over 29 squared. So you've got to remember that whenever you square a fraction, you've got to square the numerator and you've got to square the denominator. So we square 2, which is 4. All right, of course, the negative times the negative will make it positive. And then when you square the square root of 29, that's just 29. All right, then on the denominator, whenever you square 29, you get 841 And then the other fraction, you're going to square the 5, which is 25, square the square root of 29, which is 29, and on the bottom square 29 again, which is 841. Okay, so this is going to end up equaling 4 times 29 is 25, sorry, 4 times 29 is 116 over 841, and then 25 times 29 is 725 over 841. And when you add those, you can add the numerator, so 725 plus 116 is going to give you 841 over 841, which is, of course, 1, and the square root of 1 is 1. So we can see the magnitude of that vector is 1, and we just verified that, yes, we did find a unit vector, because a unit vector is always a vector that has a magnitude of 1. All right, so you guys try this one, see if you can find a unit vector for the vector 1, 1, and then use your formula to verify that it does have a magnitude of 1. To do this unit vector, we're going to take the vector 1, 1 and divide it by the square root of 1 squared plus 1 squared, because that's how we find its magnitude. So you want to divide it by its magnitude. When we divide that, we get the square root of 2. So we do 1 over square root of 2 and 1 over square root of 2. Push your square root to the top and leave a 2 on the bottom. So your unit vector is the square root of 2 over 2, square root of 2 over 2. Now when you want to verify down the bottom part that it has a magnitude of 1, so we take that unit vector and plug it into the formula for magnitude. So we got square root of 2 over 2 squared plus the square root of 2 over 2 squared. And when you multiply the numerator by itself, you get square root of 4, which is 2. And 2 squared on the bottom is 4. So both of them give you 2/4. When you add 2/4 to 2/4, you get 4/4, which is 1. Square root of 1 is 1. So we've verified that the magnitude of that vector is 1. Let me know if you guys have any questions on any of this, and I'll come around and help you. And you can go ahead and practice these problems right here on page 429.